Swayam Prabha. Digital India. Educated India.
So we are talking about the jump Markov process using master equation as a governing equation. We saw one example in the last couple of classes where we had a reaction A going to B, first order reaction, and for such a reaction we set up the chemical master equation and we showed how to solve and get an analytical solution for the probability distribution as well as the transition probability. And then continuing that sort of problems, we can also look at another problem which is very much appreciated in the context of biophysics. So in cell there are these microtubules, okay, so that is basically the integral part of a cell, and there are motor proteins, they walk on the on these microtubules, okay. So these are called motor proteins. So there's a kinesin, myosin, these are all some of the examples. And a lot of single molecular experiments have happened, okay, and the people have found that if I can represent a microtubule and the protein comes and then adsorbs here, okay, and then it actually walks in one direction, it actually sends a direction and it goes only forward, not backward, okay. And then if you look at the mechanism, the molecular mechanism of how this protein moves, basically it actually kind of extends an arm and then anchors itself, okay, and then this molecule actually comes here and then it throws another leg and then anchors here and then throws another leg. So it basically takes this kind of a discrete step walk, and people have measured that this step size can be about 4 nanometer as far as kinesin is concerned, okay. So this is a kinesin motor protein walking on a microtubule. So when measurements are done, okay, so when you look at the measurements, you will see that the position of this motor protein X, if I call that as X, okay, so it starts from somewhere here, and then you will see that its position remains constant over a period of time, because there is a time for which the molecule will have to undergo some sort of a conformational changes, and then it makes a step change of unit length which is about 4 nanometer, okay, and then it kind of spends some time here and then takes another step somewhere here and then it spends some another time and then it just keeps going. So using sort of optical tweezer or high resolution microscopy, when they look at the dynamics of this motor protein, this is a kind of trajectory that you see, okay. What is deterministic in this problem is the step height, which is pretty much constant, 4 nanometers. But if you look at the time spent in those states, okay, so if you look at this time, I call this as tau 1 and this time tau 2 and this as tau 3, and this seems to be quite distributed, it's not constant anymore. So the waiting time before the next step can happen, that seems to be a random variable, okay, with a particular distribution. So now if you want to, the question that you would like to ask is, starting from an initial condition, after time t, where would the protein be? Where is the likelihood of finding the protein be? What would be its mean position? How much uncertainty we can say about those, okay. So clearly if you want to model this as a deterministic process, you would write dx by dt is equal to some constant, okay, so it will follow a linear trend. But here in the stochastic process, we know that the problem is a stochastic or probabilistic. So we are trying to use this Markov approach to model this kind of a problem. So the question that we are posing here is, after time t, what is the position of the protein or molecule, whatever you want to call it. So effectively what we are saying is, this is a random walk, but it is one-sided random walk, okay, because it can only go forward. In the actual random walk, we said the particle can go forward or backward with certain probability, right? So here we are saying that the motion is only one directional. So we call this as a one directional or unidirectional random walk. One directional random walk. So now again we have to justify whether it's a Markov process or not. So if I'm looking at the protein at point n, okay, at some point here, and then what is the probability or what is the likelihood that it will jump to the next step depends only on its current position, okay, not the past itself, okay. It doesn't require any of its past history. It doesn't have any velocity to carry over, okay. So all these jumps are independent and uncorrelated. So the next jump depends only on the current position, okay. So therefore it is a Markov process. Actually the spatial coordinate here is a real variable, but here we are saying that the protein is actually making a step jump, even though space is continuous, but it is only occupying some sort of a lattice position like locations. So therefore we can discretize the space into a set of discrete points. So therefore we can apply the jump Markov process, okay. And if you want to do that in terms of a continuous continuous Markov process, one dimensional random walk, we can do that, but master equation is not the governing equation. We should be using the other in the differential Chapman-Kolmogorov equation. I showed there are continuous terms and there are discrete terms. We are talking about the discrete term. There is another bulky equations that describes the continuous Markov process. So we should also use that. We can also use that framework if you want to deal this problem in a continuous scale. So here we are discretizing this into discrete spatial scale. So that's why we call it as a jump Markov process, as if there is only lattice position that it can jump into, nothing in between. So we say that it is a Markov process and we say it is a jump Markov process. Then we are justified to use the chemical master equation to describe this problem. In this jump process, we have only two situations, that the position can be at x minus 1 and then it can jump to x because it increments by 1 unit length, okay, or it can be at present x and the next time it can go to x plus 1 because it can go only forward, okay. So here this event is a loss term for the probability, and this term is a gain for this probability. So there are only two terms here. Okay. And another thing you'll note here is I am using x here as the position. So this is the position of the molecule, and we use this as a discrete variable. It's a discrete variable. So the initial position is a delta function that it is starting at x naught. Okay. So initial condition we have got, the random variable we have got, and then this. So now we have to write this only for these two events. So we have dp So we have this term only when m is equal to x minus 1. Okay, because from x minus 1 it can take a unit jump to go to x. Okay, times the probability of finding at x minus 1. This term survives only for m is equal to x plus 1, because it can jump from x to x plus 1. So we have the transition probability w given at x comma t. What is the likelihood it would actually go to x plus 1 times the probability of finding x comma t. So now what we will do is that the molecule that is, when it's trying to jump, we will associate a rate a. Okay, so w something we'll say as a constant. The rate of jump or the transition probability per unit time, it does not depend on the position x or x minus 1, it is a constant. So whether it's going to be here or here, the rate is always constant. This is an assumption that we are making, because it doesn't depend on the current position. So whether it is in the nth point or nth plus 1 point, the rate of this jump is a constant. That is an assumption that we are making. Just like in the Brownian particle, when we make an assumption to jump, we say it's plus 0.5 or minus 0.5 for both forward and backward, without where exactly the particle is. Okay, so there is no spatial dependence on the rate. So that's why we say it's a constant. So basically we get okay. So this is the governing master equation for this problem. So like in the last class, to solve this, we will define a generating function. In the previous class, I defined with respect to some number n, but here I am using x. Okay, so s is a variable that I am trying to define as sum over all possible x, s power x, p of x comma t. So we do the same thing. So we are going to multiply s power x everywhere and then sum over. So here we have a s power x p of x minus 1 comma t minus a s power x p of x comma t. So this term I can take an s outside. So I'll have s x minus 1. I'm splitting s power x as s power x minus 1 times s, and s can be taken out because the summation is only over x. So this entire term is nothing but g itself. In fact, this one also, if I change the variable s x minus 1 as x, so this also becomes just g of x, g of s comma t. So we essentially have there is a here. In the previous problem, we had a partial differential equation for the chemical kinetics A going to B, but in this one-dimensional random walk, we basically get a simple linear first order ODE, ordinary differential equations. So now we can directly solve this. So you can bring g to the left and then take dt over there, and then you can integrate this. You will get ln g is equal to a s minus 1 t plus some constant c. Or simply this is e power a s minus 1 t. Now based on the initial condition, so when you use this initial condition in the definition here, so you will get this is s power x naught. So from here we see that this is s power x naught is equal to c e power just 1. So c itself, the constant c here is nothing but s power x naught. So therefore g so this is what you should get as a final solution. So generally in this kind of problem, we can take the x naught as 0, that is the origin, as if the motor protein starts from the origin itself and then moves forward. So then this simply becomes e power a s minus 1 t. So now what we want to do is we have the final solution, but we want to write this expression in this form in a sum series. Okay, any ideas how we can do that? But there is even better way to do it, right? So you can actually take this, any exponential function can be written as a sum series. Okay, so that's what I'm going to do. I'm going to split up this exponential function. So any suppose if I have something like e power ax. Yeah, so okay, let me first split this into two parts and then we'll come here. So we write g of s comma t is e power minus at times e power ast. Okay, so I'm just opening up this. And this term we can write as x ats power x by x factorial. So this e power some function can be written as sum of terms like this, this exponent time x by x factorial, and x is a index that goes from 0 onwards. So then what we need to do is we write this as sum over x s power x and at power x by x factorial. If you like, you can take also this to the inside. So now what we need to do, we go to the definition of this function g, generating function, and whatever is the prefactor of this s power x term, that should be the p of x comma t. Okay, so in the solution we have rewritten such a way that there is a s power x term and then there is a prefactor here. So this entire group of terms should be actually equal to p of x comma t. Okay, and this is, what is this? Do you recognize this distribution? So we say p of x comma t, that is the probability of finding the molecule at x at time t starting from origin, is given by e power minus at power x by x factorial. And this is nothing but Poisson distribution. So the solution of a one-dimensional random walk, or the protein walking one directionally, basically is represented by a Poisson distribution, where x is an integer. Okay, x goes from 0, 1, 2, 3 and all that. A is a constant that is describing the rate of jump, the rate of the forward motion, and t is time. So you may want to remind that in the last class we talked about a reaction kinetics, and the solution we arrived at was binomial distribution. Now we have this one-dimensional random walk giving a Poisson distribution. Both of them are actually Markov process. So from here, if you want to write the transition probability with x greater than x prime and t greater than t prime. Okay, as time elapses, the position increases. Under this condition, you can write here e power minus a t minus t prime a into t minus t prime So this is our transition probability. No, that is not the case, because the transition probability can be a function of spatial and time things. What we are only saying is it doesn't depend on the past, the history of the motion. The current probability of jump can depend on time, it can depend on the position. Here we looked at two examples. In this example, the transition probability is a constant, okay, by a factor constant a, okay. It is a most simplest kind of Markov process. The previous example we showed, it doesn't depend on the time, but it depended on the number of molecules and that state. So we say k times n. Either n is a current state variable, and the next transition probability is written as k times n. Okay. So there are other processes where we may have to say that the next time the transition probability can be a function of time also. Okay. So once we have this distribution, we can ask what is the mean. Okay, we know that for a Poisson distribution like this, the mean is nothing but AT, and standard deviation also is AT. Okay, in other words, it means that the position increases with the time linearly. Okay, this is what I said in the beginning. If you were to model this as a deterministic process, you would write dx by dt equal to some a, and the solution will give you AT, which is linearly increasing. Okay, but in the stochastic framework, we predict the same mean variations. But in addition to that, we also look at what is the uncertainty in this mean. Okay, that also goes proportional to square root of t. Okay, variance is AT, and sigma will be simply square root of AT. So the trajectory may go something like jumpy. This can be one particular realization of a random walk, one dimensional. But if you take many such many such trajectories, and then when I average over, I will get a linear increase with a slope of a, and that's what we are predicting here. Now this also goes as square root of t, so that means we have to go and represent the uncertainty here, and the uncertainty will be small, but as a function of time, this uncertainty will grow. This change is proportional to square root of t. Now, even though we looked at two different problems and two different solutions, for example, in the case of A going to B, we had a binomial distribution as a solution. For the one-dimensional random walk, we looked at this kind of Poisson distribution. But from a pure mathematical aspect, the two distributions, the binomial and the Poisson, they are also kind of related. Okay, so if you take a binomial distribution like this, so here I have this p, that's a probability of occurrence of this event, small p. Okay, if n times this capital N times p is very small, this basically can be written in terms of a Poisson distribution. Okay, so there is a proof. You can look at any elementary probability book, you will see that when this term np is very small, the binomial distribution approximates to a Poisson distribution. The reason why I am saying this is because I am going to show some experimental result corresponding to this A to B. Okay, so they did a reaction A to B in some small droplets, and then they are looking at what is the likelihood of finding one molecule or two molecule or three molecule in a given droplet. So they should be using this distribution because we know that this is the original solution. But what they did here is they found that this n times p in this reaction, this is going to be n times e power minus kt. So when this term is very small, they used the experimental data to compare with this solution. Okay, and from this solution they find if I replace this np into this is going to be e power kt, right? Yeah, so they, let's say that this is simply written as at power n, and this is lambda power at and n factorial. Yeah. So so here is droplets with certain number of reactions, 0 molecule, 1 molecule, 2 and 3, so and so. And what they experimentally found was (82.9), 15.9, this is 1.2, and then subsequently it's all 0. So some experiments were done where reaction A going to B was conducted, and then they look at what is the probability of finding a droplet with no molecules of A, one molecule of A, or two molecules of A. Okay, using some fluorescence experiment, they found these are the percentage, or these are the if you put it into 0.829, it will become a probability, but here they say in percentage. Okay, so now this distribution 0, 1, the probability of finding 0 molecule, 1 molecule, 2 molecule, etc., it actually follows nicely this Poisson distribution. By choosing a proper value of A, okay, they were able to actually compare this with a Poisson process, and they predicted something like very close to 82.8, 15.7, 1.5 and so on. So, okay, for this they have to choose a particular A value. Okay, by fitting a particular A value and using this Poisson distribution, they predicted the probability of occurrence of 0 molecule, 1 molecule, 2 molecule droplets, and that nicely captured the experimental data. This kind of data we won't be able to analyze using deterministic approach. Okay, because here the number of molecules interacting in the reaction is so small, the deterministic approach cannot lend itself useful. Okay, so this is just one example. I mean, there are many examples that you can see in literature where this kind of single molecular or very small nanoreactor experiments are held, and the results can be analyzed using in this kind of a framework. So in this approach, we derived the explicit expression for the probability distribution function of the solution. But like I said in the last class, if you don't really want this, you directly want the mean and standard deviation. You can also write the mean and standard deviation with respect to the derivatives of G and then directly get it also. So you get the same results. Okay, I'm not going to do it, but this is something as an exercise you can do. Okay.